Okay, hello and welcome back everybody. We're going to start the second half of the cosmology session. First up we have Aliso Saporo Mancini at the University of London. I'm sorry if I said that incorrectly. The talk is going to be on dark scattering, accelerated constraints from KIDS 1000 with Redact and Cosmo Power. Thank you very much.
Right, thank you very much for having me. Can you hear me right? Yes? I'll just assume that's a yes. Okay, thanks very much for having me. And so the reason for presenting this talk is the fact that it will present some computational challenges in our quest of constraining our cosmological model that I think would be particularly relevant for Roman as well. And so what this talk will be about is essentially how to get constraints on dark energy models, and in particular, in this specific case, on the dark scattering model, from weak lensing data and general from galaxy surveys data using the state-of-the-art technology in terms of nonlinear modeling of the power spectrum and emulation through neural networks. So I should say that the work that I'm going to present is has been led actually by a student from the Autonomous University of Mexico, Karim Carrion. It's been this work has been recently accepted for publication in MNRAS, so you can find all the details on the paper online that I won't have the time to discuss. So let me start actually from an introduction to Cosmo Power. So Cosmo Power is a suite of neural network emulators of cosmological power spectra that covers both the CMB and the large-scale structure. So it produces essentially CMB temperature, polarization, and lensing power spectra, and the matter power spectrum for the large-scale structure using neural networks and essentially bypassing the computation of these quantities by means of Boltzmann solvers such as CLASS and CAMB, which are typically the computational bottleneck in the evaluation of the cosmological likelihoods required in the process of parameter estimation and model comparison in cosmology. So the way this emulation is performed is essentially twofold. So the user can choose two methods to accelerate the production of cosmological power spectra, which are key ingredients in the computation of the cosmological likelihood. The first method is a simple neural network mapping between cosmological parameters and the cosmological power spectra. The second method is a mapping through a neural network of the cosmological parameters to the coefficients in a principal component analysis decomposition of the power spectra, which essentially act as a dimensionality reduction technique to reduce the dimensionality of the problem. The user can choose either method. The ultimate goal is the same, of course, which is to produce cosmological power spectra for both the CMB and the matter power spectrum in an accelerated fashion using a neural network. The code is publicly available. It's entirely written in Python, and most importantly, it's written in a way such that it doesn't require any machine learning previous knowledge in order to use it. It's really meant to be essentially a replacement, a plugin replacement of a Boltzmann code, and in fact, its syntax is actually very similar to the one that you would use to call, for example, CAMB or CLASS in your likelihood. So I just wanted to show you some example of the speedups that you can obtain by using Cosmo Power instead of Boltzmann code in your likelihood analysis. So for example, in this paper with a collaborator of mine, Davide Piras, we explored forecast constraints for a future stage 4 survey configuration, such as, for example, Euclid in terms of weak lensing. So of course, we have the problem as we move now to the analysis of these stage 4 surveys that the level of accuracy has to keep up with the increase in precision, which means that we're going to end up with a very large number of parameters to explore. So a very large parameter space to ensure that the treatment of the systematics is of adequate level in terms of accuracy, as it is the increase in precision. Which means that we need very efficient ways to explore this large parameter space. And so unfortunately, the standard approach, which is based on Boltzmann solvers, such as CAMB, for example, or CLASS, and, for example, nested sampling to explore parameter space is effectively inefficient and cannot be used on a routine basis to efficiently explore this large parameter space. So, for example, in this case, for a cosmic shear survey with stage 4 configurations, this 37-dimensional parameter space, parallelizing the inference procedure over 48 CPU cores using CAMB and Polycord to explore parameter space, this takes approximately 4 months of runtime. Whereas replacing CAMB, so replacing the source of your power spectra with CosmoPower, reduces already the runtime to just under 8 days, so makes it much more manageable. But also, because CosmoPower, and in particular, its JAX version, CosmoPower JAX, is a differentiable way by construction, differentiable way of accessing the power spectra. This means that we can now have access to the gradients of the power spectra with respect to the input parameters, which means that we can use efficient gradient-based sampling algorithms, such as the no-U-turn sampler NUTS, which is a variant of a Hamiltonian Monte Carlo, to more efficiently explore these very large parameter spaces. And importantly, we can run the algorithms on GPUs, which produces further acceleration. So for example, you can see that running the same inference procedure on in parallel on 3 GPUs, the runtime is reduced to just under 1 day, and the contours are essentially indistinguishable. So another thing that we explored, another application, was what happens if we now imagine, for example, something that at some point someone will run, which is a joint analysis of 3 surveys, which in this slide I called survey 1, 2, and 3, but you can imagine this to be Euclid, LSST, and Roman, for example, each coming with their own sets of large set of nuisance parameters. In this case, for example, we estimated for a total of 150 nuisance parameters plus the 7 cosmological parameters, for a total of 157 cosmological parameters. So a very large parameter space, which we estimated with the traditional procedure of using Polycord, for example, for nested sampling, and CAMB, for example, for the power spectra, would take optimistically 6 years of runtime to complete on using 48 CPU cores. Whereas using CosmoPower JAX, thanks to its differentiability, we can actually perform this analysis in a reasonable time, parallelizing over 3 GPUs. This takes just 3 days. So I hope I've convinced of the importance of using these accelerated pipelines. And so I'm pleased to say that the collaborations, a large number of collaborations, have started using massively CosmoPower in their analysis. In this slide, I've collected examples of applications of CosmoPower within multiple collaborations. More are ongoing. And so I would like to finish this section by emphasizing with a note to the GitHub repository for CosmoPower, which is made in a way that you can really explore the usage of this code with many notebooks that are very pedagogical and provide a thorough introduction to the code, how to train your model, how to plug it into likelihood and obtain acceleration. So please do check out the GitHub repository for many examples. Now, back to the main role of the talk, which is to report constraints on a dark energy model, which is the dark scattering model. Here, essentially the main point is that the computation of power spectra becomes even more complicated when we move away from lambda CDM. So we explore extended models. And the dark scattering is one example of this. So this dark scattering model, I won't go into any of the details of the theory, but essentially it's a Thomson scattering inspired interacting dark energy model. So there's interaction between dark energy and dark matter. It is essentially a 1-parameter extension of lambda CDM. There's an additional parameter that describes the strength of the interaction. It's related to the cross-section of the interaction between dark matter and dark energy. For all the details, you can find this on the relevant papers. So one interesting thing about this model is that depending on the sign of the interaction parameter ADS, we can get both enhancement and suppression of the matter power spectrum. This is particularly relevant in the context of the sigma 8 tension that was introduced earlier, because, I mean, essentially one of the goals of this analysis was to report constraints on this parameter in the context of weak lensing analysis, cosmic shear analysis, and see if certain values of this interaction parameter can lead to an alleviation of the sigma 8 tension. The key point, unfortunately, the difficult point in with all these dark energy models is modeling the nonlinear scales, as was also introduced earlier in Chang's talk. So for this particular case, we used the React code, which implements the Halo model reaction formalism. Again, I won't go into any of the details, but essentially the idea is that this is a mixture of one loop perturbation theory and Halo model that produces an extra factor, the reaction term, that encapsulates the response, essentially, the matter power spectrum response to the modification of gravity due to modified gravity and massive neutrinos. It has been validated up to fairly large K numbers for applications to photometric and spectroscopic surveys. But the problem is that these are very computationally intensive predictions. And so for this reason, we emulated the predictions of React using Cosmo Power in a set of emulators that have been trained by Karim. And as an example, the speed up, producing 1,000 spectra takes 0.19 seconds with the emulator, whereas it would take 8.3 hours with the original React code. So the speed up is approximately 5 orders of magnitude. The application to data was in particular to the kilodegree survey data, and in particular to 1,000 square degrees of the kilodegree survey. So this is the latest DR4 from KITS. Cosmic shear data, of course, the first step was to validate the pipeline by ensuring that the results that we obtain in Lambda CDM with the emulator are the same as the original analysis, which, as you can see, is exactly what we found. And incidentally, we obtained, again, massive speed up in terms of computation time. Then once this is done, we moved on to actually getting constraints on this extended parameter space. In terms of dark scattering, we found the KITS 1000 data to be able to constrain the parameter responsible for the interaction strength. Of course, these constraints will increase as we move towards the analysis of future surveys, for example, Euclid and Roman. We also found a mild alleviation of the tension in the Omega S8 plane. However, this is not something that it's quantitatively strongly favored by, for example, a Bayesian evidence model comparison analysis. But ultimately, this wasn't the main point of the analysis. The main point was to develop emulators that are now ready to be used with upcoming data for example, Euclid. And this is exactly the type of work that we are currently developing in terms of forecasts first, and then application to data as soon as they become available. Importantly, these emulators are publicly available, as is Cosmo Power, so I would encourage you to use it for your analysis in trying to constrain the theory of gravity, in particular with Roman, for example. Thank you very much.
Thank you very much. Do we have any questions from the audience? No? Any questions online? Okay, well, thank you. Let's thank our speaker again.